Alright, so I have problem number 1. The problem reads the chlorine in series for the function f is given by f of x equals that series on its interval of convergence. Part A reads find the interval convergence for the Maclaurin series of f, justify your answer. So the first thing you're going to do when you're looking for the interval of convergence is I always look at the ratio test, which the ratio test compares the ratio between the next term and the original term. So that's basically adding n plus 1 to your original term. So to do that, you the limit as n approaches infinity of your series plus 1. So you're adding, or your absolute value of your series plus 1. So you can get rid of the negative 1 to the n because that is all that does is flip the sign. So you have 2x to the n plus 1 over n minus 1 plus 1 would just be n. And then to divide by a fraction, you can just flip your term. So you're dividing by your original, which would just be flipping your original. So instead of writing out all the work to divide all that, I'm just going to flip this term and multiply it times n minus 1 on the bottom, because this was on the bottom and now it's on the top, and multiply the top, or take the top and put it on the bottom. And that is your base for your ratio test. And then to simplify this so you can solve the limit, you can get rid of this 2x to the n because you have 2x to the n on the top and 2x to the n on the bottom. So you can cross out 2x to the n. But you're still going to have a 2x because 2x to the first is 2x. So you're still going to have a 2x on the top. And you're going to have, forgot the limit notation.
Good call.
And then to solve this, you just look at the leading coefficient of each term. So this is going to equal 2x. So then to absolute value of, okay, I was going to get there. Then 2x has to be less than 1. The absolute value of 2x has to be less than 1, which basically means that 2x has to be between 1 and negative 1 for this to converge, for the series to converge. And then solving that, you get negative 1/2 is less than x, 1/2, or is great. So then this is what your interval convergence will be, except you have to test the endpoints because you don't know if it converges at the endpoints, which will be, you could have an equal to on either side, but you don't know. So to test your endpoints, you're going to take your original function, your original series, which is, and you're going to plug in your bounds into that function. So you're going to plug in negative 1/2 and 1/2 into your new, into your original, which for when x equals 1/2, you're going to have, and then to simplify this a little bit, this will always equal, 1 to the n will always just equal 1, so you can just cancel that out because multiplying by this. So you just have and then to test if this is convergent or divergent or convergent, you can use the alternating series test because negative 1 to the n is an alternating series. So then you're going to have your first part of the alternating series test is basically the nth term test. So limit as n approaches infinity of 1 over n minus 1 equals 0. And because it equals 0, then it passes the nth term test. Then you could do your second part of your alternating series test, which is when you're comparing the next term and the original term, and this is your original, this is your next term, and your next term is going to be less than, let's see, the denominator is smaller, this is bigger, yeah, your denominator is going to be, your new term has to be less than your original term, which in this case it is, so this converges by alternating series test. So going back to our original, when you plug in 1/2, it does converge, so we can add the equal to there, and then you have to test the other bound. So to test the other bound, you see the same thing, where you're going to add to your original function, or the original series, you're going to plug in 1/2, plug in the negative 1 to the n, times negative 1 to the n, over minus 1, and then this, to simplify this would, these negative 1 to the n would just cancel out, so you just have have 1 over n minus 1. And then to compare this, I'm going to go straight to the direct comparison test and compare it to 1 over n. And then figure out if this diverges or converges, you do the p-test. So p equals 1, which is greater than, which is just equal to 1, which means that this diverges by the properties of harmonic series. So if this diverges, and then you need to compare it back to the original function. So our original function, or our original series is n minus 1, and the comparison is 1 over n. So this, because the denominator is smaller, this function will always be smaller than this function. So like that. And because this diverges and it'll always be smaller than this, it'll always be under that function. So this diverging means this also diverges. So then this function diverges by direct comparison test. Then going back to our interval convergence, we would not put the line there because it diverges. So this is our fully found interval of convergence, which is solving A, and your justification would be your testing your endpoints and your ratio test. B reads, show that y equals fx is a solution to the differential equation x times y prime minus y equals 4x squared over 1 plus 2x for the interval convergence found in part A. So your y is your original summation, which will just be -1. And then your derivative with respect to x is going to be this function, but you're going to multiply the power times the function, so that n times 2x, and then subtract 1 from the power over n minus 1. So now you have the two parts. You have one more step to do and multiply your y prime times x, and what you're doing is you're adding an x into this, so you're adding an x to the first into this this numerator. So x to the first, it combines with 2x and n minus 1 to just be 2x to the n, because your minus 1 and your 1 would cancel out and be opposites of each other. So then your function will look like this, and then combining those summations and factoring out, you can take factoring out like terms. You can have 2x to the n over n minus 1 times n minus 1, because this whole thing will just be left with just the n once you factor out. This will only be left with just the minus 1. So then you'll have this. Then you cancel out your n minus 1 and your n minus 1, which means you're left with the summation of to the n, and you combine those terms to be negative 2x to the n. And this is a geometric series. So a geometric series can be simplified, written as a over 1 minus r. Your a is your first term, and in this case, when you're starting at 2, which is in the original problem, you're plugging in 2 and you're gonna get 4x squared equals a, and your r is the rate at which it goes up, which in this case is negative 2x. So you're gonna have a, which is 4x squared over 1 minus negative 2x, which equals 4x squared over 1 plus 2x, which is the original proof for the problem. Right here.